Okay, this is where we finished last time with our tie-in to the derivatives. Again, we were talking about how to find extreme or relative minimum or maximum values. And what we looked at here is saying, well, all we have to do is determine...
Would a custodian please call extension 203? Custodian 203.
Yeah, no custodians needed to call 203. Anyway, what we needed to figure out here was when the first derivative equaled 0. And again, the way we did that, the reason we did that was back here looking at these problems because we realized that if you take the derivative here, we can figure out that has a horizontal tangent line. The same with this one. This one ended up with two possible answers. X was 0, X was 2. And we were able to do that and determine there was a relative maximum here and a relative minimum here. And again, relative means kind of in that area. Again, just in that area, that's the highest point. And down here, that's the lowest point. But for this one here, this is again an extreme because that is the lowest point. The graph doesn't get any lower than that. And again, we solve for the x values to determine the minimum and maximum values. Now, the next thing you're going to see is an extremely important definition, so I will give you guys some time to copy it down. That's the definition of critical points. Now, critical points are going to be the most important thing that you learn in Chapter 3. So let's get them the first time. First of all, let's say we have a function f, and it's defined at a point C. So think of a function, a polynomial function, and we have some point C. I'm looking at an x-coordinate, x equals C. If the derivative at C equals 0, or the derivative is undefined at that point C, if f prime of C equals 0, or if f prime of C is undefined, then C is a critical point. It's that straightforward. Here's what you're going to end up doing. To determine critical points, take the derivative of the function, set it equal to 0, set it equal to undefined, and then to realize that those are the critical points. This portion of it's going to become very important when you deal with rational functions. And don't forget again, if you have a rational function, we'll say numerator x over denominator x. If we have a numerator function over a denominator function, and we take the derivative of it, and let's say this is n prime over d prime, we'll set that. This is f, correction, this would be n prime of x. We would set that equal to 0. And then that would tell us where that equals 0. And we'll set d prime of x equal to 0 to figure out where it's d and e. Again, we can't have 0 on bottom, but we can have 0 on top. The critical point theorem is talking about that same function f, and if f has a relative max or min at x equals c, then c is a critical point for function f. This is where it's very important. Then c is a critical point for function f. That's very important. Let me explain to you what this will look like. If I pull up some graph here, and let's say we graph the following function, like this. All this, that function, correction, all that theorem means, right here, what this function means, if you have relative max or mins at points, we have a relative max here, ooh, bad color, we have a relative max here, we have a relative min here, and again we have a relative max here. What this means is we would end up having a critical point here. We would end up having a critical point here. Again, this is one x equals c. This is another x equals c. And we would end up with a third one here at x equals c. This function would end up with 3 critical points because there are 1, 2, 3 humps on this polynomial function. And again, don't forget some of the basic stuff here on this polynomial function. Both directions going down tell me, first of all, the fact that they're both going in the same direction tells me it's an even power. And the fact that they're going down tells me it's a negative leading coefficient. So, don't forget some of the basics. But again, this function has 1, 2, 3 critical points. Here are the steps for how to determine the extrema on a closed interval, AB. So now, instead of looking at a function for all values, we're only looking at it on a closed interval from A to B. It's actually a very straightforward process. First steps, determine all critical points in AB. So what you're going to do is take the derivative of it. Again, don't forget, if you don't have anything, take the derivative of it. Take the derivative of your function and see where it equals 0 and see where it does not exist. And again, does not exist parts, if you're looking at a rational function, that's the bottom. If you're looking at a trig function like tangent, you can have some vertical asymptotes, and there's some other functions like that as well. Next, you're going to evaluate the function f at each critical point in AB. And I'll go through what I'm talking about here. Let's say we end up with a function x equals 2. Let's say in our interval, we figure out we have critical points at x equals 2 and x equals 4. What that means here is that you're going to plug 2 into the function f to figure out the y-coordinate. Then you would plug 4 into the f function and figure out the y-coordinate. The next thing we're going to do is figure out what are the values at the endpoints. When I say evaluate, I'm just really meaning here coordinate pair. We're just figuring out the coordinate pair. But we want to do it at the endpoints as well, because don't forget, it's a closed interval. Closed interval, AB. The lowest value is the minimum. This is the y value. The highest y value is the maximum. And it is possible to have multiple maximum or multiple minimum values. So it's more or less a 4-step process. I'm going to walk you through one of them, then I'll give you guys some time, and then we'll go through a couple more of these. Alright. For instance, on this problem here, again, the first step, figure out f prime of x, which in this case here is 3x squared minus 12. And what we have to do is figure out where it equals 0 and where it equals dne. Well, the dne part is easy because this is a polynomial, so its domain is all real numbers, which is not darn. Again, the domain is from negative infinity to infinity, so we don't have to worry about the dne portion. But we do have to worry about this. Now let's pull a 3 out, and we're left with x squared minus 4 equals 0. And then we'll end up with 3. And where does x squared minus 4 equal 0? That's x plus 2, x minus 2 equals 0. So I have critical points at x equals negative 2, correction, x equals negative 2 and x equals 2. However, we're going to throw out one of these because my bounds only go from 0 to 4, so I'm not going to include negative 2 because it is not within our bounds. So our critical points are at x equals 2. So step 1 is done. Step 2, evaluate the function f at each critical point in AB. So what we're going to do here is figure out f of 2. And again, we're plugging it back into the original function. This becomes 2 cubed minus 12 times 2, which is 8 minus 24, which is negative 16. So that tells me I have a point here at 2, negative 16. And that's step 2. So step 1 is done. Step 2 is done. Step 3, evaluate the function at the endpoints. So for step 3, we have to figure out f of 0, because again, we're right up here again. my endpoints are 0 and 4. So f of 0 will be 0 cubed minus 12 times 0, which is 0. So that means I have a point here of 0, comma 0. And then my other endpoint is f of 4, which will be 4 cubed minus 12 times 4. 4 cubed is 64 minus 48, which is 48, which would be 48, 58, 16. Took me a moment. So this point is 4, comma 16. So now we have 3 points then. Let's make that a little bit lighter. Okay. So we have 3 points. Here's one possible point. Here's a second possible point. And here's a third possible point. And now we need to go back and figure out the lowest y value is the minimum, the highest y value is the maximum. Well, this one has a negative 16, so this is the minimum. This one has 0, this one has 16, so this is the maximum. Again, over that interval, and this is just a point. It is a nothing. This is just some point on the interval. So our minimum value over the closed bounds from 0 to 4 is negative 16, and our maximum value over the bounds 0 to 4 is 4, 16. And again, that all goes back to this problem here. All right. Now, you guys know how to do some of these. I'm going to give you a problem to look at, and I want you to try to see if you guys can do it. This is the problem, 3x to the 4th minus 4x cubed on the interval from negative 1 to 2. I'm going to turn this off. I want you guys to see if you can come up with the extrema for this. So, good luck.